All right, so is this record? Yeah, I think I'm recording. We are looking at rational functions. We're including their intercepts, but we're also reviewing the end behavior, the vertical asymptotes, and the holes of a graph. So let's find the intercepts. To find the y-intercept, we're going to let x equal 0. So remember y, the function notation f of x is just the new notation for y. So we often say that we're plugging in 0 into the function. The principle of substitution is what you're doing. If x is 0, well, the whole numerator is 0, but so is the whole denominator. And 0 divided by 0 is undefined, so this graph has no y-intercept. This graph will not cross the y-axis. What about x-intercepts? Well, to find x-intercepts, we let y equal 0. And we know that a fraction will reduce to 0 if the numerator is equal to 0. Now, so the numerator controls it, and I focus my attention on the numerator. However, I can't completely ignore the denominator because if they share a common factor, the numerator and denominator, it's going to create a hole. And if I'm not careful, I'll end up calling a hole an x-intercept. Well, a hole, your graph doesn't pass through a hole, so how can I say that it's an x-intercept? It can't be both. So you've got to be careful. Here I notice that an x is the greatest common factor in the numerator, and I factor this to x squared minus 8x minus 9. The denominator x is also, so there I have a common factor that is going to reduce. Now I can continue to factor this x minus 9 and x plus 1. So I know that x equals 0 is not the domain of this function, that I can't set here when I cancel this denominator. Like I say, the numerator controls whether this reduces to 0. But I do not want to call x equals 0. Well, we know it had no y-intercept, so it can't. If x equals 0, that's saying it's passing through the origin, and it can't pass through the origin. So there's another reason, a warning sign that, hey, x equals 0 is not an x-intercept. Now, if we set the numerator equal to 0, we do have that 9 and negative 1 are going to be x-intercepts. So this graph will intersect the x-axis at x equals 9 and at x equals negative 1. It will not intersect the y-axis at all. We've seen here with this cancellation, when we know that when we get to the holes, there's going to be a hole in the graph at the origin, but we'll point that out when it asks us for that. So let's move on. So I'm going to clear this. Thought I cleared it. Yeah. What am I doing now? End behavior. So the end behavior, I compare the degree of the numerator against the degree of the denominator. It's top heavy. The degree of the numerator is greater than the degree of the denominator, so there is no horizontal asymptote. So the end behavior of this graph, as x is approaching negative infinity, we need to determine, is y approaching positive infinity or negative infinity? As x is approaching positive infinity, what is y doing? Is it approaching positive or negative infinity? So the easiest way for us to do this is to plug in extreme values. Values very, very small, heading towards negative infinity, and then values very, very large, heading towards positive infinity. When you do that, x to the third is king of the mountain. It becomes so much larger than well, in the case of negative infinity, so much smaller that these other terms don't even affect it. It's just a grain of sand versus an entire beach. Now here in the denominator, same idea. This x squared, the term with the largest exponent dominates the other terms. So if we're trying to figure out what's going on with y as x is becoming very, very negative, we look at this ratio. We're going to have a negative number that's raised to an odd power divided by a negative number that's raised to an even power. That ratio will be a negative number divided by a positive number, which is going to be negative. So I know my end behavior on the left that as x is going to negative infinity, the y values are also going to negative infinity. Now what about when you move to the right of the graph, when you're very far to the right of the origin, as x is approaching positive infinity, what's going on? So as these values become very, very positive, very large, what do we have? Well, we've got this large number that's being raised to the third power, this large number that's being squared, and that's a ratio of positive numbers, so that's positive. So I know that as x is going to positive infinity, as x is getting larger, so is y. It's going to positive infinity. So this is my end behavior. Alright, now what does it want? Vertical asymptotes. So we look at the reduced fraction. We factor and see if we can cancel any terms. In the numerator, we already said that x, we factored this earlier, that x minus 9, x plus 1, I believe. Yeah. And then here, x and x minus 2. So the x's did, factor of x did cancel. So I focus my attention on the denominator of my reduced fraction to figure out vertical asymptote. So this graph does have a vertical asymptote. And if you set the denominator equal to 0, it's easy to see the solution is x equals 2, that 2 minus 2 gives me 0. So this vertical asymptote is a vertical line, and it's a line x equals 2. You want to give your answer in the form of an equation, not just the number 2. This is representing infinitely many points. A vertical line at x equals 2 has infinitely many points. Alright, so then it wants us to identify any holes in the graph, right? Yeah. So the factors that canceled, they produce a hole, because see, you're removing that from the domain. Anything that's removed from the domain of a rational function on the graph will appear as a hole or a vertical asymptote. So the 2 got removed from the domain. It appeared as a vertical asymptote. The 0 is being removed from the domain. It's going to appear as a hole. To determine the y-coordinate of the hole, if I plug the 0 back in the original function, I get 0 divided by 0, which is undefined. So I have to plug 0 into this reduced fraction and see what I get. Well, in the numerator, I get negative 9 times a positive 1, which is just negative 9. And in the denominator, when I plug in 0, I get a negative 2. So the negative divided by negative is going to cancel, and I just have 9 divided by 2. So that's all they wanted. There's our answers for number 2. I hope that helps, and I'll talk to you later.